Yes, you can start.
Good afternoon, everyone. A warm welcome to all of you to the fourth talk of a mini-series on Lie Algebras. A warm welcome to Professor Ilangovan, who is a spokesperson of all the four lectures of our mini-series. We also have Professor Satya with us. Welcome to you, sir. So before we begin our talk, there are a few instructions for the audience. At the end, when you are supposed to ask the questions, feel free to ask your questions and please don't unmute yourself until and unless you are asked to do so. You can also write all your questions in the chat box or use the raise hand option feature in the Zoom. For those who are live on YouTube, you can ask your doubts using chat box and we'll make sure that all your questions will reach to the speaker. Thank you, sir. Over to you, sir.
Okay, thank you. Thank you very much. The final talk of the series. So, human beings always are fascinated about whether life exists elsewhere in the universe, and it is always a fascinating thing to see unidentified flying objects, UFO. When I was young, people used to call it as flying saucer. I don't know nowadays what people got. But in general, UFOs are spotted quite a lot. All of you might have had experience spotting UFOs, and well, you might have seen these things many times. It goes this way, sometimes above. So generally in classrooms all over the world, UFOs are spotted, and I am telling this today because this is the last lecture. Let us see whether any UFO is going to be spotted in our lecture. Okay, so yesterday at the end I was defining this Cartan killing form. For arbitrary Lie algebra, this is the main tool. K of xy equal to trace of add x add y for every xy in L. And this is the main theorem. For simple Lie algebras, this Cartan killing form is going to be non-degenerate. And conversely, if it is non-degenerate, it is direct sum of simple Lie algebras. And that is called a semi-simple Lie algebra. So semi-simple Lie algebra is nothing but direct sum of simple Lie algebras. So the statement of the theorem essentially is that for a Lie algebra, the Cartan killing form is non-degenerate if and only if it is a semi-simple Lie algebra. Okay, but all these calculations so far we have been doing for SLN. This is what we had got. Okay, H is the diagonal matrices and L alpha is the eigenspace corresponding to the eigenfunction alpha, and this is what we have had for SLN. Okay, and I wrote down the roots also once. Maybe we'll visit it some other time during this lecture. So what happens in general? What happens in an arbitrary simple Lie algebra? Here we had naturally diagonal matrices which worked out very well, and SLN we could write it as H direct sum L alpha in H star. So what happened here? SLN is decomposed as H, and all the eigenspaces corresponding to different eigenfunctionals F. So this is the main idea behind what we are going to do in an arbitrary simple Lie algebra. So we define what is known as a toral subalgebra. The idea is exactly coming from this. What do we have for the diagonal matrices? The whole space decomposed into eigenspaces. So that means every element of this diagonal, they are all odd also is diagonalizable. So that is what has happened here. We generalize whatever happened there, and that leads to add T being diagonalizable for every T in T. Okay, so this is the subalgebra that is going to help us carry out whatever we were doing in SLN to arbitrary Lie algebra. And further definition, we did not stop with just finite now. I mean, a few of the diagonals, we took all the diagonals. So we have to take a maximal toral subalgebra. This maximal toral subalgebra is called Cartan subalgebra. So one question, of course, we have defined it, of course, for arbitrary simple Lie algebra. Arbitrary Lie algebra we have defined. And the question is this. Answer is yes. If L is M. For a semi-simple Lie algebra, toral subalgebras always exist. Okay, as I said, today UFO spotting will mean a lot of results are going to be quoted without much proof. So this is a very, very deep theorem. It goes beyond SL2 in some sense. Many of the other things which I am going to state, they will all follow from the SL2 theory what we have developed. And once we have a toral subalgebra, since we are in a finite dimensional setup, yes, any doubts?
No, sir.
Okay, fine. Yeah, so because it is finite dimensional, from a toral subalgebra, you can always construct a maximal toral subalgebra. And this is what is going to correspond to the diagonals in SLN case. That's why I denoted the same thing by H, the same notation I am using. So now, by definition, add T is diagonalizable for every element here. Okay, add T is always diagonalizable, and that is why we can write L as H direct sum L alpha exactly as before. I am putting a question mark there, H. Okay, one of the important things, In the case of diagonal matrices, we saw that all those linear functionals that exist in L alpha, they were all non-zero. That is why I put a question mark here. Let us have a definition. The obvious definition for a subalgebra, we can define centralizer to be all the elements with Lie bracket x comma t equal to 0 for every t. So in case of SLN, it so happened that centralizer of H was itself, because all those L alphas were non-zero. And this is again a theorem. This theorem, of course, again is a lengthy proof, but it keeps on using repeatedly what we have been talking about SL2 theory. SL2 theory only will keep on repeating. And of course, the other thing which I have defined, the Cartan killing form, that is going to play an important role also. This is our definition of Cartan killing form. A of x equal to trace of add x add y, and this is the claim. The killing form satisfies this property. First, you take the Lie bracket xy and then take z, or you take yz and then take x. These two are going to be same. This is the claim, and as you know, add xy is going to be add x add y, because add is a representation. That is something we will use. So let us write both of them one by one. What is k of xyz? This is trace of add xy add z. This is same as trace of add x add y into add z. Okay, add is a representation, it's a Lie algebra homomorphism. So add x bracket y is same as add x add y bracket, and add z is there. So this is nothing but trace of add x add y minus add y add x into add z. So this is how the abstract structure we have managed to get out of by using the adjoint representation. We know what is add x comma add y because we are in GLL in the linear transformations or matrices. We know that Lie bracket is precisely add x add y minus add x. So what do we get? This is trace of add x add y add z minus add y add x add z. So this is what we have on the one side. on the other side we have k of x, y bracket z.
Sir, we cannot see the current board.
Fine now?
Yes, sir.
Yeah. So add of y, z, I am putting it as add y, add z. This is same as trace of add x, add y, add z, minus add z, add y. So this is trace of add x, add y, add z, minus add x, add z, add y. So the first term is same in both the things, trace of add x, add y, add z. The second one is, in that I should write it here, maybe it's for convenience of everybody. This is what we had got, trace of add x, add y, add z, minus add y, add x, add z. Okay, so if you see these two terms, first term is same. Like a second term, what has happened? Add y is appearing in the front in one and at the end in another. And we know that trace of AB is trace of BA. So that is why these two are equal. Add x, add z is, you can take it as A, add x, add y, you can take it as B. So you can see that these two are equal. Okay, so killing form satisfies this important property. And in our particular case now, let us take H in H, X in L alpha, Y belonging to L beta. What this tells us? This tells us that X comma H Y equal to X comma H Y. Okay, this killing form satisfying this property is true for every X, Y, Z. I am taking specific examples now. H is the Cartan subalgebra, maximal toral subalgebra. X is coming from L alpha, Y is coming from L beta. What does this give us? X comma H is what? It is minus alpha H. H bracket Y is beta HY. X is in L alpha, so HX is alpha HX. We have XH, so it is minus. So if I take the things out, what do we get? Minus alpha HK of XY equal to beta HK of. So alpha H plus beta H times K of XY. So in this particular case, this is what we get, alpha plus beta of H times K of XY 0. So if Vikram, so what we get is something like this, alpha plus beta of H K of XY equal to 0. So suppose alpha plus beta is not 0. Okay, so suppose alpha plus beta is not 0, alpha and beta are two linear functionals on H. Suppose alpha plus beta is non-zero, there exists some h in h such that alpha plus beta of h is non-zero. If a linear functional is not zero, that means at least at some point it is non-zero. And for this particular h, what this gives? This tells us that k of xy is 0. And this was for every x in L alpha, y in L beta. As long as alpha plus beta is not 0, Killing form from L alpha, L beta, this is going to be 0. Okay, so this is a very, very important step in making some progress here. So what do we know? But K is non-degenerate. We know that K is non-degenerate. So if alpha is there, if L alpha is non-zero, if L alpha, the eigenspace exists, if L minus alpha is not there, the whole thing is going to be 0. So this is what is happening. If L alpha is non-zero, L minus alpha also has to be non-zero. Okay, so this is a very, very important step that we are making observation from the simple property of Killing form. If L alpha is non-zero, L minus alpha is non-zero. And again, by using SL2 theory repeatedly, and show that C alpha, LC alpha is non-zero if and only if C is present. We can also show that this any scalar multiple, if you take, it's going to be non-zero if and only if alpha C is plus or minus 1. No other multiple is going to be a root. This will follow from all the SL2 theory I have written. What theory? The irreducible representations of SL2 that we discussed yesterday. Okay, we can keep applying it to get this kind of a thing. So what we are driving at now from L is arbitrary simple Lie algebra, H is maximal toral subalgebra, then L can be written as H direct sum L alpha, where these are all not zero. And for every alpha occurring here, scalar multiple is there only when scalar is plus or minus 1. And more things are true. What are the other things true? So let us take this P to be set of all alpha and H star for which L alpha is not zero. Okay, so various properties are going to be satisfied with this set phi. We have taken all alpha in H star for which L alpha is not equal to 0. So from a simple Lie algebra, we are moving to some linear functionals. So phi is set of all alpha in H star for which that eigenspace L alpha is non-zero. These are all the properties that are going to satisfy. I will just mention them. Zero is not there and it's going to span. In SLN, of course, we have seen we had H1, H2, Hn minus 1, and we had alpha 1, alpha to alpha n minus 1. So they will all be linearly independent, and we can get this. For every alpha in phi, the only multiples of alpha in phi are going to be plus or minus alpha. Okay, so before coming here, I should have mentioned something. What is this bracket now I am talking about? We are in H star. So let me mention this. We know that the killing form is non-degenerate on L, and we also saw that K of L alpha L beta is going to be 0 if alpha plus beta is not equal to 0. And H is basically the L0 in that notation, what we call a centroiser of H. So K is going to be non-degenerate on H itself. See H, if you take K of add H, add X, all other L alpha, it's going to be 0 because of the same reasoning. H is what is going to be L0 because H is abelian. This is what is going to happen, and K L alpha L beta is 0 if alpha plus beta is not equal to 0. In particular, K of H L alpha will be 0 for every alpha non-zero. So only place where it's going to be non-zero is going to be coming from H. And using this, so that is what I am denoting by this. What we had is a killing form on the Lie algebra, and since it satisfied various properties of non-degeneracy and L alpha L beta equal to 0, it became non-degenerate on H. Once something is non-degenerate on H, we can lift it to H star. Okay, I suppose everybody knows this kind of a thing. We have a non-degenerate form on H, can be lifted to H star. Basically, what it is going to say, alpha of T beta may be equal to Lie bracket alpha beta. So that is what we are using here. And then the last property, for every alpha beta in phi, alpha minus 2 alpha beta by beta 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 is going to be in phi. Again, these properties 3 and 4 are all going to follow from the SL2 theory only. We know that in a SL2 representation, all the numbers occurring are going to be integers, and we also wrote down for irreducible representation, if highest weight is n, n minus 2, n minus 4, etc., it's going to go all the way to minus n. So that is all what we need to get these properties. And so far we were talking about everything over complex numbers. Now we restrict our attention to the real vector space, and by we don't have to bother about the complex vector space anymore. We can decide to restrict ourselves to just the real vector space, and one more property, we can call it as theorem. K is positive definite. I have mentioned that K is non-degenerate on H. That followed easily from whatever we have done. But it also happens that it's going to be positive definite. And so what we are getting is an inner product. It's no longer just any non-degenerate bilinear form. It is actually an inner product. And in the inner product, we have phi satisfying these four properties. So we started with an abstract simple Lie algebra using adjoint representation and the killing form. We are able to get some finite set in Rn with the inner product space satisfying all these properties. So this is what leads to an abstract root system. So if we have now from complex numbers, or for that matter any algebraically closed field over characteristic 0, we are able to come to a real vector space which is an inner product space, and all these phi satisfying all these four properties. So this is called a root system. So this way, classifying simple Lie algebras was our problem. We have changed it into a problem of classifying root systems. Okay, of course, when I'm happily casually saying these things, lot of things have to be checked. Any two Lie algebras, when I take this corresponding root system should be different, and so classifying root systems will automatically, we have to go back both ways. We have to be able to go. Given a simple Lie algebra, we should be able to get, we have got a root system, that's what we have seen. And given any root system, we should be able to go back to get a simple Lie algebra also. Those kind of things are all left for the time being. So what all we have done is to shift the problem here. We make just one more definition. So we define a root system being irreducible if it cannot be written as union of two non-empty sets, where if I take an element alpha from here and beta here, alpha beta equal to 0. So such a thing we call it irreducible. Irreducible means it can be done. So basically it becomes a union of irreducibles, as you can see otherwise. So if we started with a simple Lie algebra, root system obtained will be irreducible. Okay, so simple algebras actually correspond to irreducible root systems. So we have to classify irreducible root systems. This is what we have brought it to. I must tell you this, all of you know that Galva is a youth icon of maths. He was just 19 and he proved a lot of things, so he is a big youth icon. And in our subject, there is E. Carthon. So E. Carthon was only 22 and he finished his PhD, and that too not an ordinary PhD, one of the best PhDs that has been produced in the world. At the age of 22, he managed to classify all the simple Lie algebras. I should make one more point here. It's very unfortunate that yesterday I was telling you how calculations are important. People should not be like Zamindar and become snooty towards calculations. But Okay, it's unfortunate that mathematicians do talk very loosely about some things they don't like. I have heard stories. Okay, so somebody says analysis is wrong, somebody says combinatorics or analytic number theory, they are not mainstream as. So this is all something you should take it with not just a pinch of salt, but with the load of salt. As you see, so from classifying simple Lie algebras, we have brought it down to some finite set maneuvering. So please understand that you don't know when what will be useful in mathematics. So this is my request to all the students. Okay, instead of caring about which area is better, kindly use everything as mathematics. This is all mathematics. So now what tool we are going to use? So if you notice something, when we were writing these roots in SLN, so this is what happened when we were writing the roots of SLN. Alpha 1, alpha 2, alpha minus 1 we take. All of the ones which were above the diagonal, they all had non-negative coefficients, and all the ones below the diagonal, they all had non-positive coefficients. Okay, that's why everything looked very, very beautiful in case of SLN. So this is the model we want to copy in general. So that leads to this definition. We call a subset a base, and the elements there are called simple roots. If, of course, first, let us say, sorry, it's in Rn. Deltas should span Rn. So we have lifted our idea from the SLN and we define what is a base. The elements of delta are going to be the simple roots. Of course, first it has to span Rn, and every element we have to be writing as a linear combination of elements. All the coefficients should be non-negative, or all the coefficients should be non-positive. And again, as always, the question occurs whether such a thing exists. Answer is yes. Okay, so for any root system phi, a base always exists, and sorry, I make one small mistake. There should be a base is not just spanning is not enough. Should be a basis of. Alright. Okay, so now if I take alpha beta in delta, what do I know? I know that alpha minus 2 alpha beta by beta beta beta, this is an element of phi. By definition of phi, I know that this is going to be a root. Okay, so this is going to be a root, and sorry, this is a bracket. If alpha beta is greater than 0, what does this mean? Alpha minus 2 alpha beta by beta beta is written as linear combination of elements alpha beta in delta with one positive coefficient and one negative coefficient. Because if alpha beta is 0, minus 2 alpha beta by beta beta is negative, and alpha has the coefficient 1, and we know that this is not possible because delta is a base. For a base, every element of phi should be written with all non-negative coefficients or non-positive coefficients. This mixing is not allowed. So alpha beta is always less than or equal to 0 for any 2 beta. Of course, I am assuming alpha not equal to beta. Maybe I should have here also alpha not. So when I take two different simple roots, the inner product is always less than or equal to 0. And in an inner product space in R2, if you see, we know that this alpha beta is mod alpha mod beta cos theta, theta angle between alpha and beta. So alpha beta less than or equal to beta means theta is. We cannot have an acute angle. If it's an angle is acute, we know that cos theta is positive, but we know that alpha beta is going to be less than or equal to 0. It's always up to, or maybe 90 degrees allowed, greater than or equal to pi by 2. That's what I can say. Okay, so with all this discussion, what we are going to do now, From root system classification, we are going to move to totally graph theoretic ideas. This is what is known as Dynkin diagram. Dynkin diagram is a directed graph, and how we are going to define it? The vertices correspond to a simple root and the number of edges between alpha and beta is this number 4 alpha beta square divided by so this is the number which we are going to number of edges between alpha and beta is going to be this. Keep it here only. Okay, so but what is this number actually? If you see here, alpha beta is and alpha mod beta cos theta. So this number 4 alpha beta square is 4 mod alpha square mod beta square cos square theta. This is what it is, and if I divide here, you know that 4 alpha beta square divided by mod alpha square beta square 4 cos square theta. So this number is precisely 4 cos square theta, and theta is an obtuse angle. So all these are going to become, so this number is between and this is an integer, okay? Most importantly, this is a being a square, it's a non-negative integer, but since it is 4 cos square theta, and we are not taking the same thing, alpha is not equal to beta, so cos theta cannot be 1. So the number is between 0 and 3. This is what it is. And this way, we have shifted the problem further to classifying Dynkin diagrams. From simple Lie algebras, we move to root systems, and from root systems, we have come to Dynkin diagrams. So just as an example, let us see SL n plus 1. Let us say n plus 1. See, SL n plus 1 is what will correspond to AN. That's why I'm writing n plus 1. We had the H1 like this 1 minus 1. This was H1. And if it was 1 minus 2 minus 1, this was H2, etc. So this was alpha 1. This was alpha 2. This was alpha 1 plus alpha 2, alpha 1 plus alpha 2 plus alpha 3, alpha 1 plus alpha 2, etc. Alpha n. This was alpha 2, and this is alpha 2 plus alpha 3. This was alpha 3, etc. This is alpha n. These are all elements of H. Just above that, it's coming alpha 3 plus alpha 4, etc. And these are all the negatives, minus alpha 1, minus alpha 1 minus alpha 2 minus 2, etc. Okay, so in this case, what happens to the Dynkin diagram? So one thing about the roots that we had mentioned, alpha minus 2 alpha beta by beta 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 is always a root. So if alpha beta is less than 0, we will always get alpha plus some k beta, k positive. Okay, so you can see that alpha 1 plus alpha 3 is not a root. Because alpha 1 plus alpha 3 is not a root, the inner product between them will be 0. Alpha 1, alpha 2, there is a root, so that will be minus 1. So it turns out like this, alpha 1, alpha 2 is minus 1, alpha 2, alpha 3 is minus 1, alpha 3, alpha 4, minus 1, etc. Alpha n minus 1, minus 1, and all other 0. I mean, alpha 1 plus alpha 3, alpha 1 plus alpha 4, etc. Alpha 1 plus alpha n are not roots, and so on. Okay, so all these things are not roots, and because of that, the inner product all will be 0. And some normalization we have to do. So what we get is something like this. This is what we got an. This is what is SL n plus. Okay, the 4 classical Lie algebras I already mentioned. This is what comes to an. What is bn? Bn is here. There's going to be a 2. I didn't mention what this arrow is. I will tell you soon. See, these were all the classical Lie algebras. An corresponds to SLN plus 1. This corresponds to orthogonal odd dimension. This is eclectic. This is orthogonal even dimension. Okay, for all these things, so nice thing is this. These are all infinite families of simple Lie algebras, and all these things are already known to everybody. The beauty is that something new happens. Okay, those 4 were infinite ones. They are all the classical Lie algebras. Then we get exactly 5 exceptional ones. So E6, E7, E8, F4, G2. These are the 5 exceptional ones we get. And now the job is to retrace the whole thing. First, see A and B and C and D, and already I told you they all come from classical Lie algebra, so we didn't have to retrace the steps. These 5 exceptional ones, these are the Dinkin diagrams, and using Dinkin diagrams, we should go back and construct root systems. Then from the root systems, we construct simple Lie algebra. Exactly 5 exceptions. That is a nice thing about this theory. Of course, all this proof is nothing but combinatorics. The whole proof of verifying that these are the classical ones, these are the things, all these diagrams are the only ones coming. This is all combinatorics. There is no Lie theory naturally involved. Lie theory stopped once we got a root system. From root system, using simple roots, we move to Dinkin diagrams, and Dinkin diagram classification is only combinatorics, nothing else. Say I'm running out of time. I want to tell you a couple of things quickly. Some of you must be knowing swimming. Some of you may be knowing cycling. So if you learn swimming and cycling, even if you don't do it for 10 years, still after 10 years you will remember it, right? It's not that just because 10 years you did not do swimming or cycling, you are going to forget it. And that's the same thing with mathematics. Okay, mathematics, when you learn how to think independently, you learn how to think originally, you learn how to do free thinking, and still there is a discipline in your thinking, and that is what will stay all your life. Okay, that is if you don't continue in academics. If you are going to continue in academics, I'll tell you something quickly. If you are going to be in academics, your knowledge base is what is going to be your bank balance. So keep improving that, and before you are 30, it gets difficult. It's not that it's impossible or anything. Definitely at my age, it's even harder. As you grow older, it will get harder and harder to learn different ways of thinking. So before you are 30, try your best to learn as many thinking as possible. And the last one, this is a quote from Lenin. Learn more, learn more and more. There is no end to learning. So with that, I am stopping. Thank you very much, Curry Leaf people, for giving me the opportunity to give all these 4 lectures. Today's lecture, of course, we had to do so much work because final classification is done. Anybody, any questions? Chat box, anything is there?
No, sir.
Chat box, nothing.
No, sir. Thank you so much, sir, for giving us such a knowledgeable talk. Lastly, we will have a group photo at the end. So you all are requested to turn on the camera.
Mr. Alapan was the one who was in touch with me from the beginning, and he has been missing. I don't know where he is.
Okay, sir, I will ask him after the session.
No problem.
Yeah.
Yeah.
Okay, so I'll count 3, and on the third count, you all are requested to smile, and we'll have a photo. Okay, 1, 2, and 3.
Thank you.
Thank you, sir. So lastly, I would also thank Professor Vikram, who is with Professor Ilangovan and giving us a technical support about making, ensuring us like the camera is clear and we all are able to see the board very clearly. We thank to you, sir. We also thankful to Professor Ilangovan, who has spared out his time and has made such a big effort to deliver insightful talk and making this mini series a success. We look forward to more opportunities to learn from you in future, sir. And lastly, I would also thank to all the audience for being the part of the mini series. And a special thanks to the backbone of this mini series, that is MTTS Trust and all the organizing members of Kareli. Thank you, sir.
Thank you. Thank you very much. I will clap also.